Today, we're going to pull back the curtain on the single most important piece of software you own, the operating system. You can think of it as the silent conductor, this mastermind manager working behind the scenes, making everything you see on your screen even possible. I mean, think about it for a second. Every single click, every key you press, every application you open, it's all being managed by this incredibly powerful and pretty much invisible force that's running the entire show. And that force, well, that's your OS. So, what's the official definition? Well, an operating system is really the essential foundation that lets you, the user, talk to your computer's hardware. It manages absolutely everything from your memory to your printer, making it the bedrock of your entire digital life. Okay, so where does all this work even begin? Well, it all kicks off the very second you hit that power button. Let's trace that journey, from a simple press to a machine that's fully up and running. So before anything else can happen, your computer gives itself a quick checkup. This is what we call the boot up sequence. It runs something called a power on self-test, or post, just to make sure all the essential hardware is connected and working like it should. Only after it gets the all clear does it finally load the main operating system into memory, getting it ready for action. Now, there are two key players managing this whole startup show, the BIOS and the device drivers. Think of the BIOS as the initial inspector. It is the very first program that runs, and its one and only job is to do that initial hardware check. Once the OS is loaded, that's when the device drivers take over. They're like universal translators, allowing the OS to have a proper conversation with every specific piece of hardware, from your mouse right down to your monitor.
Okay, the computer's on. Now for the real magic. How in the world does a computer with just one central processor run your web browser, your music player, and a dozen other things in the background all at the same time? The answer, my friends, is scheduling.
Basically, there are two main ways to think about this. Non-preemptive scheduling is kind of like a polite queue. Once a task starts, it runs all the way to the end. But what if that task is huge? Well, everyone else has to wait. That's exactly why modern operating systems, like the one on your phone or your laptop, almost always use preemptive scheduling. The OS acts like a super fast manager, constantly starting and stopping tasks, giving each one just a tiny slice of processor time. It happens so fast that it creates this perfect illusion of multitasking. And this is where it gets really interesting, right? Let's look at a couple of common algorithms. First come, first served is exactly what it sounds like. It's simple, but it has a massive flaw. If a really big, slow job gets to the front of the line, everything else just grinds to a halt. Round robin solves this. Every single program gets an equal, tiny little time slice. This makes sure every app feels responsive, but the trade-off is that those really long tasks get chopped up and can actually take a lot longer to finish overall. So the OS isn't just a time manager, it's a space manager too. Your computer has a pretty limited amount of super fast physical memory, what we call RAM. So how does it run these massive programs that are way bigger than the RAM itself? Well, this is one of the OS's most clever tricks. You know, the best way to think about this is with an analogy. Imagine your RAM is a small desk where you can work really quickly. Your hard drive, on the other hand, is a massive library. The OS acts like a super fast librarian. It breaks your programs down into these equal-sized chunks called pages, like pages in a book. And it only keeps the pages you're currently working on right there on the desk. The rest? They stay in the library, ready to be swapped in the second you need them. This whole process is called paging. So paging is all about splitting memory into equal physical blocks, because that's super efficient for the OS to manage. But there's another way to do it called segmentation. With this method, memory is split into logical blocks that actually reflect how the program is built, like a chunk for a specific function or a loop. So you could say paging is about what's easy for the OS, while segmentation is about what makes sense for the program. And the secret sauce that makes all of this swapping possible? That's called virtual memory. The OS basically carves out a piece of your much slower hard drive and just pretends it's an extension of RAM. This is what creates that incredible illusion of having nearly infinite memory to work with. But this whole system has a breaking point, and you've probably felt it. When you push your virtual memory too hard, you get something called disk thrashing. It's when the OS is spending so much time swapping pages between the hard drive and RAM, our librarian just running frantically back and forth to the library, that it has no time left to do any actual work for you. And that's that freeze you feel when you have way too many browser tabs open. Okay, so we know the OS is juggling tasks and memory, but what happens when something totally unexpected demands attention, like right now? Like you moving your mouse or a file finally finishing its download. Well, that's all handled by interrupts. An interrupt is basically a signal from hardware or software shouting, "Hey, I need you now." Think of the CPU as a chef who's really focused on cooking a complicated meal. An interrupt is like a waiter running in and handing them a new urgent order. The chef has to carefully pause what they're doing, mark their exact spot in the recipe, handle that new order, and then come right back to the original meal exactly where they left off. And this whole process has a name, of course, the interrupt service routine. It's built right into the CPU's core rhythm. So here's how it works. After every single instruction cycle, the processor checks for interrupts. If there's a high priority one waiting, it saves its current work to a special memory area called a stack. Then the processor goes and handles the interrupt. Finally, once it's done, it grabs its original work from the stack and continues on as if nothing ever happened. It's this constant, incredibly fast cycle of work, check, and respond. Now think about it. The OS on your laptop is kind of like a jack of all trades, right? It's designed to do a little bit of everything. But some jobs, they need a specialist. So let's explore some very different kinds of operating systems that are built for very specific jobs. On one hand, you have an embedded OS. It's built for one specific job, like running your microwave or maybe a digital watch. It's small, it's low power, and it just does its one narrow task perfectly. Then on the other extreme, you have a real-time OS, and this is all about deadlines. It's used in systems like self-driving cars or hospital life support, where a task must be completed within a guaranteed timeframe for safety. In that world, there are absolutely no excuses for being late. And the list goes on. You've got distributed OSs, which spread a single massive task, like analyzing data from space telescopes, across many different computers, combining all their power. And then you have multi-user OSs, which do the opposite. They let tons of people share the resources of one incredibly powerful computer all at the same time. But maybe the most mind-bending idea of all is the virtual machine. This is where software is used to emulate an entire computer system from the ground up. I mean, it is literally a complete, fully functional computer that's just running as another program on your actual computer. Okay, but why on earth would you ever want to do that? Well, one massive reason is protection. A virtual machine acts as a kind of digital sandbox. You can run suspicious software or test for viruses inside what's called the guest virtual machine. And even if it gets completely wrecked by malware, your real host machine remains perfectly safe, completely untouched by all the chaos happening inside. So from waking up the machine to juggling countless tasks to literally creating entire virtual worlds inside itself, the operating system is, without a doubt, the unsung hero of computing. It's the conductor of this incredibly complex orchestra, which, of course, leaves us with one final thought. If the OS is the conductor, what happens when it drops the baton?